Okay, welcome back everybody. Just in the interest of time, I think we're going to start the next session for today. There's 3 talks, and this is in the FAIR platforms and interoperability section. So this is, I think, trying to see FAIR and open in action. And our first talk in this section will be Ari, talking about building fair environmental service platforms in Europe. And just as a fair warning, I'm going to set the clock for 25 minutes.
Okay.
And then we have 5 minutes for questions.
Sure.
For
Try to be a little
speaker.
bit strict.
Good. Okay.
Thank you.
Yeah.
Thank you. So I'm Ari Asmi. I come from ICOS ERIC, which is one of the research infrastructures in Europe. The head office is in Helsinki. I also work in University of Helsinki. And so what we are working in here is that the previous 2 talks were very much on quite high level, I would say. We go a little bit lower, closer to actual practicalities, but not yet really on the practical level. So what I'm going to talk about is environmental infrastructures. First part of the discussion is for the people who are not really aware of what research infrastructures are and what the environmental infrastructures in Europe at least are. I will explain it a little bit. And then I will explain about this new initiative, what we have from our perspective, from the environmental sciences perspective on the fair data and fair data services. So let's start with the European environmental research infrastructure. You can maybe not see so clearly, but there is some pictures of these ones. They usually are big facilities or things which are available for many kind of researchers. And what is important to notice that in Europe, these things, they are not run by, or they can be a part of some sort of university or something, but the infrastructure side of it is taken out, and it is a service provider for researchers. So it's not a thing like if a Moscow State University has a nice laboratory, it would mean that that laboratory would have been taken as such that anybody could come and visit that laboratory. So that's the concept of European research infrastructures. Of course, the idea behind it is that individual researchers don't have the money in their grants to pay for all their facilities. These things have started from things like CERN in Switzerland or the European Southern Observatory, huge facilities. But in the environmental sector, we are usually talking about distributed ones, which work in several places. You have different kind of observations or laboratories distributed across Europe. They serve a wide variety of researchers, so you don't have just one group which is behind there. Important thing for the FAIR things is that they are long-term organizations, meaning that they are not meant to be just running for a single research program. They are meant to be running for decades. And then, of course, they have a constant connection to their user groups, which also means then that they can act as a kind of representatives in some cases for quite large area of research users. They usually give physical access and or data access, and they are, when they're operational, they are their own legal entities, meaning that they are not part of any specific university. For example, I'm working in the Integrated Carbon Observation System, ERIC. ERIC is a legal entity. It means that it has its own budget, its own director, all these things. And so how the researchers usually access is that you can have either really passive data access, so the infrastructure RI here makes some observations of nature, environment or something, they provide data, and the researcher passively accesses it. Then there's another way that the researcher can, for example, tell the infrastructure that I would need now somebody to do this kind of experiment. They do it and they give the data to the researcher. Or there is even a possibility that the researcher is somehow remotely, virtually controlling some sort of experiment. This is a bit rarer right now, but it's coming more in the future. And then, of course, the completely different access method is the kind of traditional physical access. So you have a synchrotron somewhere, and then the researcher travels there to do the experiment, and so on. But for the data side, this side is usually more relevant. What we have done for the last 8 years, we have quite a few of these infrastructures. I will show you in a moment about this. There should be more pictures, but for some reason they didn't show up. So for the last 8 years, these infrastructures in Europe from different fields of environmental sciences have worked together. And we decided that it's a very good idea to work, especially in the case of data side, but also for technical observation, mechanisms and metadata and all these kind of things, to work together and try to make things together. And we have created a lot of different kind of policies and formats and so on, which we agree on. And we produce our products in this way. And these are of course funded, very much supported by European Commission. And this is, right now we have 25, actually a bit more, a couple of had just joined, more than 25 this kind of pan-European infrastructures working together, creating environmental standards and policies. So this is a little bit old map, old picture, and the projector isn't the best possible, but I'm just briefly saying that you can see a lot of logos. Each one of these logos is a major European network of usually about 10, 15 countries across Europe doing some sort of either observations or providing services. We have things which are working on a biosphere or ecosystem side. We have things on the atmospheric observations. This is a big radar, for example. An actress is doing in-situ observations near ground for air pollution. Then there's marine domain observations, different kinds. And then of course solid earth, and some of these work in several of these domains at the same time. ICOS is there, but also ESNS, for example, is one which is doing climate simulations. So you can have really an e-infrastructure as well in the environmental field. And some of these are experimental, meaning that people do experiments. Some of them are observational, meaning that you have a network of observations across a large area. And then some of them are virtual, meaning that they are basically working mostly on collecting either data from other places or providing some sort of environmental calculations. Now, challenges in environmental field, I'm not saying these are unique. These kind of challenges happen in other fields as well. But really, one of the problems in environmental field is that there is so many different disciplines working in there. So you have, and the science questions vary, and the scales which things are observed and analyzed are different. So you have stratospheric physics and ecosystem behavior, or microorganisms, or then earthquake observations. All of these are working in very, very different fields of sciences. And disciplines, they have tendency to create their own language and working culture. And then sometimes even communication between these different disciplines is quite difficult, even in the infrastructures which are long-term worked already together. And so, of course, in how people work, there are differences in formats, working culture, or maturity of the infrastructure, depending where you are working. But however, the problem in environmental field is that in some other fields, this is not so big problem. If you have in physics, people are working in neutron physics different way than in synchrotrons, it's not necessarily that huge problem for their problems. But for environmental science, this is really an issue. That if the things don't work together across the different disciplines, we can't really solve a lot of our questions. So just briefly, if you could think that we are usually measuring in science, we like to put ourselves in the little boxes, disciplinary boxes, which are even smaller than these ones. So you work in a little piece of atmospheric research. But actually what environment is, you have these environmental challenges, and especially societal needs, which don't really match any of these disciplines. And you can think it like a cube, that if you just wonder one little piece of here, it's really difficult to answer any societal questions, which is usually what environmental field is about. There is no measurement network for food security. You need to have observations of a lot kind of things and experiments, a lot of kind of things to answer these. And so if you don't really collaborate and create this kind of play or create the system, at least on the data, or preferably in the service side, that these ones would work together, you will have very narrow service and very big difficulties answering any of these societal challenges. So that's the background. So this is where we have worked this far. And now I'm going to talk about a little bit on our next project, which is a bit more directly connected to the last previous two talks. And it's also connected to this FAIR and European Open Science Cloud. Fairness and environmental infrastructures. Before I start, there's a couple of things what we learned from the couple of previous ENVI projects what we had. First of all, if you want to create something new with your data system or something, it's not very good idea to separate the computer scientists from the domain scientists. Because I usually have this dog and cat analogy that it's very hard to get them to work together, but if they grow together, then they are happy together already in the long way. Because we have this experience that if you have somebody from the top saying that this is the best solution for everybody ever, like computer scientists, I don't know, maybe everybody in the room is computer scientists, sorry, but they have a little bit of tendency of creating a huge solution which solves everything, and then you come into the domain scientist and they are saying this is not what we want, this is not something which works. And so it's a good idea to have this kind of co-design. So you work together and try to working together, trying to find the best solution, which kind of fix these things, maybe not the most elegant solution in the whole world, but it works. And so this top-down method doesn't really work. And what also you usually need is a hierarchy of standards, which is how we built this new project as well. Meaning that if you we talk about FAIR, and we talk about what is findable and accessible and so on. So as you saw in Simon's talk, right now we are very abstract level. When you're talking about all sciences and everything, findability is a fine word, but it's kind of vague. And if you go much more into more individual disciplines, you can define this much more. In environmental field, you can define it already a little bit more clearly. Then you go in the subfield of environmental field, you can really say that now you have to follow this and this and this and this standard. And you can be more and more accurate to more, let's say, smaller field you go in. So just briefly, ENVI FAIR project, which we hopefully will be, we are already in grant preparation, so most likely it will start in January 2019. It's a 4-year project and it's coordinated by Research Center Jülich in Germany, but the co-coordination is University of Helsinki and me, and we have 47 partners. So I don't want to bore you with this kind of project management details, but what we actually do in the project, I will show a couple of slides in here. How much time do I have?
You have another 10 minutes.
Okay, well then I can even slow down a little.
We have lots of questions.
Yeah. So there's two main axes what we do. We try to create common standards, but also common policies. The difference is standards. What we think is these are not standards. We are not going to ISO to make something, but our community standard. Let's say these are technical things. These are things how we think that. If we say PID, identifier, what do we mean by that identifier? Which identifier and how what kind of metadata model we should use? This policy side is a thing which is also quite interesting. It says that when you say accessible, what does it actually require for your access policies? It requires certain things you have to create in your organization, saying that okay, we accept that people can get this into this facility or this service using certain kind of standardized way of accessing it. This is, I think, now, of course, it's very easy to say when you're not doing things. I'm not a computer scientist, so I think that all these standards are easy and the policies are hard, but it might be a completely different way when you're a computer scientist. It's a very common thing. But anyhow, the idea is to develop these two, train the infrastructure staff on these standards and policies, and then also implement, together with some help from the IT experts, these standards and policies into their services. So creating really implementational services, and this shows a little poorly here because of code choice, and then the idea is that select few of them in the European Open Science Cloud as operational services which are provided for all the services. With their requirements and what are in the Open Science Cloud. some basic concepts. The infrastructures themselves do the implementation, not somebody from the outside. I think this comes from the cat and dog explanation. That you need this one to make sure that you also can, if you change a lot of things in the services and you lose the connection to the user communities, then the infrastructures are no longer used. You can have a really fancy, great system, but nobody wants to use it. We also try to use external services when needed, but all the solutions what we want to make are such that we can change the service provider as easy as possible. We have to agree on the common access policies and other policies related to this fair data, or what the fairness means. And this is what we consider to be the border control, that if you want to be in the environmental infrastructures and you are saying that you are providing fair things, we are trying to define these ones. What this reusability actually means in practice for us. And then we have this hierarchy approach, what I said. The cluster level means now the older environmental infrastructures. Subdomain means like marine infrastructures have their own standards, which are more detailed, and then individual infrastructure level can be even more detailed. And then one important thing why I'm also talking here is that all policies and standards have to be considered with external stakeholders, which means also other countries, because environmental science is not something what only Europeans do. And it doesn't make any sense whatsoever that we have our own standards, how we do and things. It has to be something where at least there is a dialogue or some sort of way of making them consistent. There is also another thing which was mentioned earlier, which is Copernicus services, for example. That's a big external user for our data, and we have to make sure that if we want to change our access policies, they are not at least in conflict with Copernicus, because they are one of our customers. So we have to make sure that all these external things work. So just briefly, this is from our proposal. I wouldn't want to go to details, but really we are aiming not only to, I mean, of course, you can just have raw data and then add a little bit of metadata, but we are really aiming towards providing service level things from these infrastructures. So it is much harder, and these are actually quite well connected to these F, A, I, and R of the FAIR, that many of these reusability requirements actually come in the service level. And that is, that I cannot promise everything what we produce will be made completely reusable and interoperable across the whole domain, but we are working as much as possible on this. And then this kind of horrible state diagram in the end, which is how the project is built. So we have here, well, we have in the beginning coordination management, but I think it's quite important to notice here is that we have this kind of community strategy where the infrastructure leaders, directors sit and they discuss with them what is the strategic level. Then we have the policy work where we try to find common policies, and that feeds into standards. And these, of course, have to work together. So if the policies say something which cannot be really done in technical sense, that's important to know. Then what is also important to understand is that in here, we have for different fields of science, we have implementation work packages, which are quite directly connected to the stakeholder or the standards development. And of course, there is support activities for this. And this is just to make sure that everything stays consistent. And it's very important to keep the lines running there. And what this is my last slide. What I wanted also to say about this connection to other things, you can see these are kind of stakeholders what we have to take into account in this kind of activity. Of course, you have to talk to the European Commission, but then you have to talk about the Research Data Alliance, which was mentioned earlier, and CODATA and so on. Then, of course, European Open Science Cloud, it's one of the clients. Scientific user communities. This is a big difference sometimes. When you have people talking about European Science Cloud, they think about it from the top and thinking that this is the greatest thing ever. But frankly, I've seen sometimes of these kind of big programs where people come from the top and say this is the greatest thing ever, and nobody has ever asked do the researchers actually want this kind of thing. So this is a thing what we really also are aiming at. Of course, some public relations are needed, but in the Europe also, what is very important for us is the connection to the member states. You can do a lot of things in the European level, but if the member states, Germany and France and so on, are not interested, it will not run for long. And then you have things like Copernicus and things like in here. And also other clusters. This is something that I wanted to mention, is that we are not working in environmental field alone. Similar cluster projects are funded in physics, astronomy, social sciences, all these different fields of research in Europe. And we are doing collaboration with them to make sure that overall things stay consistent. This is especially important in the environmental sector, in biochemical, biomedical and food clusters, because there is a lot of overlap with these ones. Sometimes some of the infrastructures are kind of providing for them. So that was basically what I had to present here. So it, as you can see, I didn't go into any standards what it actually means to be fair. But this is what we are now trying to build from a little bit from the disciplinary side. So environmental research by nature needs this fairness, and many of the, so we really need for this interdisciplinarity in data and services, not only in data. But the very nature of this field makes this hard. And the research infrastructures can be a tool in here, because if you talk to individual researchers, they have a limited scope, individual projects are short-timed, but the research infrastructures stay for a long time in Europe at least. And we have been active community for a long time, and the new project is trying to create these standards and policies, but we need to really communicate with the researchers and specialists from all around the world and different fields. So that's what I had. Thank you.
Okay, we have 5 minutes for questions.
One question. When you present features, for example, this one, okay, this one, common fair policies. For me, this is impression that this is something for human.
Yes, it is.
Yes. I'm looking if there are any compliance of your plans with application plan of European expert group to make reality. They propose to make these policies document objects processed by computers. Are you going to this direction?
In some senses, yes. If you are talking about things like, of course, actually how we split these ones is that these kind of policies, we define what we require, and then the kind of realization comes from the standards work, but it doesn't really matter in that sense. But for example, one of the policies which we definitely are aiming at is machine readability, that you need to have your system and services such that, for example, the licenses are machine readable, that every time that you get this access to, which is actually should be relatively easy in environmental field, because we basically use one license. So it makes things a little bit easier, but because everything in an environmental field, you don't really do secret observations. In biomedical side, you are in a completely different situation with personal protection and so on. But I think the license will not be the tricky part. My guess is that the tricky part will be there is some services which are resource limited. So you need, for example, computational resource. And making common policy with this one is a bit challenging, because to tell you the truth, we can do a lot of things in environmental or in the European level, but who is going to pay for these services is member states. So we need, every time that we want to make some sort of new fancy policy, especially which requires actually money transfer, we need to talk to them. and then that gets it gets a little bit more challenging after that. But this is really the policies. This could also lead fair politics. So this is much.
With the standards, etc.
Yeah.
I'm looking how more complicated it will be finally.
Hopefully not too much. Yes. The thing is that what I really love about plans is that the plans look always simple and everything goes nicely. But I know, I've been in so many different projects that we will know that actually, as I said, at least from my perspective, this part, the technical solution, especially when it's done globally together with RDA and so on, I'm pretty sure we'll find solutions here. In here, we might really get in trouble sometimes. And trying to also, at the same time as this is happening, the European Open Science Cloud is quite separately doing their own policy recommendations. And then there's also other policy recommendations coming from different sides, and trying to merge all these together in something consistent is, and at the same time they're asking us our opinions, which is very hard because the project starts in January. So it's a bit trying.
Mostly it will be.
Yes. Yeah.
How much time you have to, how much time you need to spend on the procedure of the standard meeting?
So how long?
How long is
Yeah, it's going to run actually for this. This is not ISO standards, just to make sure. These are community standards, because ISO standards take like decade to
it?
get.
It was not an international standard.
No.
Only
Pe-
for standard for this community.
Exactly. Because we cannot.
Procedure only on data, not information and knowledge.
No, most likely not. Because the point is, of course, we can be part of this kind of international standard building. This is not a problem. But we perfectly well understand that we have commission money for 4 years, and in 4 years you are not going to get any kind of ISO standard anywhere. So I mean, you can start the process or suggest things, but it's not going to become ISO standard.
Yep, time for one last question.
You mentioned about external stakeholders.
Yeah.
These organizations, they have some agreement, or should they pay money?
No.
Or what are formal requirements to these external stakeholders?
There is actually not really that much of formal requirements. What we really want to do is to create a very good way of communication, and that's why, in principle, you can draw a memorandum of understanding or something, but there definitely is no money required.
And they receive the access to data of this.
I mean, this is the good part of environmental data, is at least in Europe, is that how these infrastructures are built, everything is freely accessible anyhow. So what we need the stakeholders now is to tell us that if they have some really conflict, that for example our standard is very, Europeans create some sort of fancy new standards for some observations, and then Russia has been using for 40 years something else. And so then it might be good to know at least that this actually exists, and then we can think that would there be a way of doing this in a better way.
Thank you.
Okay, thank you, Aaron. Okay, next I would like to have Sergey come to the floor. Okay, and maybe you can queue up your own slides. Okay. Yeah, and Sergey will be talking about fair data based on extensible unifying data model development.
Okay.
Okay.
Good afternoon, dear colleagues. So, actually, this session is entitled Fair Platforms and Interoperability. And Ari told us about the platform, and now for the next two talks, we are moving to general issues of interoperability. So, and my talk is devoted to the techniques of data model unification. We consider this technique as a stage of data integration as a whole. So I'm going to overview this data model unification technique and to show somehow the place of this technique within the fair data platforms. So to start with the outline, I will start with the data integration as a whole, with the motivation, some levels of data integration, and some points of data integration within fair data principles. And after that, I will proceed with overviewing of data model unification technique with the extensible unifying data model design, with languages and formal methods which are required for construction of data model mappings. I will show the main stages of constructing the mappings of data models, and I will conclude with some example of our work in this direction, and with some discussion questions concerning canonical data models for fair data infrastructures. So let's start with the motivation for the data integration as a whole. So actually nowadays we live in the world of huge amount of heterogeneous data sources. And what does it mean heterogeneity for us? Heterogeneity means that these data sources are represented in very different data models. There are some examples of these quite different data models, from traditional relational model supported, for instance, by SQL standard, to various kinds of NoSQL models, document, array graph, semantic models like OWL and RDF, and so on. And all these heterogeneous data sources are usually placed in some data infrastructures. And what would we like to do with them? We would like to solve some problems over these heterogeneous data sources within these data infrastructures. And for sure, we should provide some methods and tools to make these heterogeneous data sources reusable and interoperable. And that's the the fair data principles. Within the data integration as a whole, we can distinguish at least 3 levels of data integration. So the most high level of data integration is the data model integration, which is called unification. So we have to match on this level. We have to match the elements of data models as languages. So, for instance, on this picture, we are trying to match the elements of UML model and relational model, to match the elements, attributes of these models, and so on. So the next level of data integration is schema integration, when we match data types or structures and their attributes. And on this right hand side picture, we're trying to match 2 abstract data types. First is books, and the second is books, book info, probably from different databases, from different schemas, and defined in different languages. So we're trying to establish a correspondence between these data types and between their attributes. And the last but not least level of data integration is data integration proper. On this level, we're trying to transform the source data from source data collections, their elements and attribute values into some objects or structures that conform to some source schemas. So usually completion or the integration on the high level is really a prerequisite for the integration on a lower level. So you can see that, during this talk, I'm going to talk about this high level, which is devoted to data model integration or unification. As we can see, any level of data integration makes data more fair. Well, obviously, integrated data is much more easier to find, access, and reuse, and so on. And this integration makes data, actually makes data interoperable. Well, if these heterogeneous data sources are stored in different databases defined in different data models, and actually there are a lot of approaches for data integration, but from our point of view, the most major level of data integration is achieved with such kinds of data integration systems like subject mediators or data warehouses. Well, I'm not going to go deeply in the details of data warehouses, but let's proceed to the next slide, and I will show in some high level the some stages of data integration within subject mediators. This kind of integration is called virtual. So we have a subject mediator. Well, in this statement is a data integration system. So and user communicates with data integration system, and user defines like queries or problems or workflows in terms of schema that is defined for this subject mediator. And the subject mediator as an integration system is connected via wrappers with maybe a lot of heterogeneous data sources. So a query or program formulated by user is transformed into subqueries. These subqueries are passed to the resources, transforms to the queries that are able to be executed on these resources. Then these subqueries are executed on the resources. The result is transformed into form that conforms to the schema or the mediator. So these results are transferred to the subject mediator, combined and sent back to the user. So this is the idea behind the data integration. And nowadays we can consider that all these heterogeneous sources are placed, for instance, in some data infrastructure, and we can consider the all this zoo of resources in data infrastructure as a data lake. Well, it's a term that is quite popular right now. So let's go back to the previous slide. And one of the main ideas behind this the data integration technique with virtual integration is that this data integration is truly based on some unifying data model. So we called this data model canonical, and all source data models have to be mapped in these unifying data models, and we called this that in this way they are unified with this canonical data model. And surely this data model unification is prerequisite both for metadata integration and for data integration and interoperability and reuse within fair data infrastructures. So actually for both kinds, for virtual integration and materialized integration in data warehouses, the data model unification techniques can provide a truly formal basis. So let's proceed with the data unification part. So the main idea behind this data model unification is the principles of constructing the canonical or unifying data model for some data integration system. Surely nowadays, well, this zoo of data models, as I showed you on the first slide, well, this zoo is quite heterogeneous, and so we cannot provide some common data model that can that is able to cover all the data models in the world. So what the main idea for this technique, that this unifying or canonical data model should be extensible. So well, these extensions of the canonical data model can be based on some specific data structures, on data types, or on some compound operations that are not predefined in this canonical data model, or on some restrictions which can be expressed as dependencies or axioms. So, well, the main idea behind the construction of this extensible unifying data model is that for every source data model, for instance R1, we construct the appropriate extension of the kernel of the canonical data model, which is called here E1. And this extension should be constructed in such a way that there is a semantic preserving mapping from source data model to the extended canonical model. And in the heterogeneous environment of various resources, this canonical model is formed as a union of the kernel and all the required extensions. So that's the idea of the synthesis of the canonical data model for some integration system. So what does it mean for some concrete data model that that this data model is unified with the canonical data model? So first, for some source data model R, as I said earlier, we have to construct the extension E or the our kernel of the kernel of our canonical data model. The second step is a creation of the mapping M from the source model R into extended canonical model. And well, last but not least, we have to formally prove that this mapping, well, is truly semantic preserving. Well, this term refines or refinement, it's a formal term, and it's well, on very high level, that truly means that while this mapping, the information and semantic of operation is preserved. So this means that we construct the mapping in a proper way. So and we have to provide some possibility of proving that for every schema S that conforms this source model, it truly refines its image under the mapping M. Well, so and if we are able to prove to formally prove this fact, well, in a proper way, we suppose that we really unify our source data model R. So, what languages on this slide? I'm discussing what languages and formal methods are required to support this data model mapping. Surely, the first important thing is a kernel of the canonical model. In our research during last years, we applied as a kernel of the canonical data model a specific hybrid semi-structured and object-related data model that is called the synthesis language. But surely, and I will discuss it on my last slide, there are several other possibilities, and all these techniques are able to be applied for other kinds of kernels of the canonical model. Well, the second thing are formal methods that allow us to describe data model syntax and data model semantic mappings or transformations or of one model to another. We applied during the last years, we applied two approaches for that. The first approach is based on meta-compilation languages. On these meta-compilation languages and term rewriting, and it is supported by the specific pack of tools called a meta-environment. And the second approach we used is based on model-driven architecture methods and tools on eCore metamodel, EMF text framework, and Atlas transformation language. So, and the last thing required for constructing data model mappings mentioned on this slide, well, is methods and tools for supporting verification of refinement. For this we used a specific formal language. It is called abstract machine notation, and it is based on the first order predicate logic and set theory. And this language is supported by technology and tools for proving the refinement formally. And it's called, all this technology behind this language is called B technology. So, using all these tools, actually, the mapping of the resource model into the canonical model can be divided in some stages, and on this slide, well, I underline the main point of these stages. What should we do? What steps should we proceed to construct the proper mapping from some source model into canonical data model? So the first step is a formalization of the resource model syntax and semantics. And the formalization of the source model syntax we called reference schema. And this reference schema actually is some abstract description which contains concept, and these concepts are related to some constructions or elements of the model, well, and some association or relationship among these concepts. Well, the second stage is the integration of reference schemas of source model and canonical information model. So it's like a matching of elements of one language, source language, and canonical data model language. So the third stage obviously is the creation of the required extension of the canonical data model. After that we should construct the transformation of the source data model into extended canonical model, and finally we have to verify that the extended canonical data model is refined by the source data model. So I think on my next maybe about 10 slides, or these slides are devoted to these steps, well, in more wide way, but I think I do not have so much time, so I will show it in a glance, I should say, yes. So the first stage of the constructing of this mapping, well, is a formalization of syntax. So, well, within next maybe 10 slides, we consider a unification of web ontology language with the our object data model. So, firstly, we have to take some formal document with formal syntax and represent with the syntax with neglecting all the syntactic sugar by some reference schema. Also, we have to formalize the semantics of our source model. So in this way, we have to construct the formal mapping of the source data model into our formal language, abstract machine notation. So we have to provide some mechanisms that will give us for all schema represented in source data model, our here, which will provide us the formal specification in abstract machine notation. The next step is a matching of the reference schemas of source data model and canonical data model. And here on the upper side of this slide, you can see some UML diagram with elements of web ontology language. And on the lower part, you can see some also some UML diagram which describes some elements of our object model, and all these lines shows us the correspondences between these elements, and all these correspondences have to be combined in some table with the well, proper corresponding of elements, their attributes and relationships, and so on. And after that, we have to construct, if it's required, we have to construct some extension of the canonical model to represent some elements or some constructions which are presented in the source data model. For instance, it's in OWL, it's a transitive association or transitive relationship, and initially it's not represented in our object data model, so we have to extend somehow with a special construction called association meta class. And after that, we have to construct the transformation of the resource model into extended canonical model. So first, we have to automatically generate the template of this transformation on the basis of the correspondences between constructions of resource and canonical models, and on the basis of reference schemas of this model. And some elements and transformation rule templates can be constructed automatically, but also this transformation will be not complete, and this transformation have to be completed manually by expert, and expert have to extend or modify these transformation rules. Well, and finally, according to the definition of this transformation, the specific program code is generated automatically. And the final stage of construction, this provable data model mapping, is a verification of this mapping. So using this semantic transformation from source data model and canonical data model into abstract machine notation, we can reduce the refinement problem formulated in terms of source data model and canonical model, and reduce it to the problem expressed as specification in abstract machine notation. And to finally prove or not prove or this fact of refinement, we can apply specific automatic or interactive proof systems. So
Yeah,
I do have
Sergey, you got 4 minutes.
4 minutes. Okay, I have only 2 slides. Okay. So last but one slide. So actually, we applied all these mentioned techniques during the last years for unification of actually quite various zoo of data models, from workflow models, semantics models, various NoSQL models, array, graph-based, and so on. And actually, maybe it's a question for discussion. Well, after the lunch, one of the main questions there actually behind this presentation is, but very important question, is choosing the appropriate kernel or the canonical data model for the fair data infrastructures. Well, we can see at least 2 candidates. For instance, SQL and RDF. There are some pros and some contras, but actually that's a great issue to discuss. Thank you.
Okay, we have a few minutes for questions.
Do you face limitations in terms of the extension of your kernel so that it remains pragmatic to be used?
Yes. Well, according to our experience, actually, we can cover some wide range of data models. Well, truly, we cannot guarantee that we can cover all this stuff. But we can try to provide some trying to maybe to invent some mechanisms or to use some mechanism. Or for instance, for SQL and RDF, we have to use some conventional extension mechanism that are embedded into these models. So.
Can these mappings be automated?
Yeah, these mappings. The main aim that all these mappings have to be automated.
Yeah.
But in the process of the construction of these mappings, this process cannot be automated totally. And some involving of expert is required fully.
Okay, great. There's one more question here.
In this sphere, we can talk about reading information from different sources. Yes, that?
Yeah.
Or writing the information to the different sources. Could you write some information to different sources? Different types?
Well, actually, that's a tricky question. But actually, I started with the data integration systems. At least 2 kinds: virtual integration supported by subject mediators, and materialized integration supported by data warehouses. And actually, it's not the aim of the data integration system to update data in data sources. So that's just a reading and integrating problem.
Okay, very good. Thank you, Sergey. We will cut it there. And now I think we hear from Nikolay. So you need to upload your... Yeah, okay, please. So Nikolay will tell us about meaningful data interoperability and reuse among heterogeneous scientific communities. So very much related.
where it should be copied.
Yeah, I don't know. Sergey, do you have a preference for the document goes, where the PDF would go?
It is okay.
Just send it desktop.
Разрешения просто нет.
Куда?
А,
Куда?
куда? Там папка не было. Сейчас. Погоди. Ну ты сам в буфер скопировал?
Нет.
Ну скопируй в буфер. Не будет копировать. Убери с экрана. Сейчас изменился, что ли? Только что было здесь. Не. Куда папка? Вот здесь папка была. А, открой вот здесь, смотри. Вот.
I will give you a signal at 25 minutes.
Okay. I will be focused on interoperability in research data structures and the role of communities in it. The role of communities and formal specifications of domains. I will talk about fair data principles in research infrastructures and their consequences for using formal specifications of subject domains. I will show without details an example in astronomy where we solve an amount of problems. Then talk about role of method specifications and experiment specifications in infrastructures. And I'll finish showing research life cycle based on formal specifications. There are some research that cannot be based on old principles of research because of huge amounts of data or heterogeneous methods applied. But there are also many research groups that hold old principles and their research process may consist of searching for heterogeneous data sources in their research domain. Then integration of those data sources, research itself to discover some new knowledges, and they finish on heterogeneously represented results. There are many problems based on such approach, because every time we begin a new problem solving, we should find data and integrate it to an environment we use to solve the problem. We could not add new data sources if they appear in time, because we should rewrite programs, and we don't support reuse of our results and reuse of implemented methods for similar problems solving. Fair data principles is kind of initiatives to solve some of these problems. They are inherited from data curation principles and aiming to make data interoperable and reusable. To make data fair, it should be well identified, comply to known data models, specified with metadata and provenance. And when but fair data principles are defined not formally, and as the result we see many kinds of interpretations, from ratings of conformity to applications of application of known linked data principles to provide fair data. Another initiative is for solving the mentioned problems is investigations in research infrastructure. Which organize access to multiple data sources, and support collaboration of researchers. When we try to apply fair data principles to research infrastructures, we see that fair data should be readable by humans as well as machines. So we should specify that data and services so that it is possible. That's why I focus on domain specifications, and specifically formal specifications of research areas. It may include ontologies that specify concepts and relations used in a domain, and conceptual schemas is a different notion which focuses on requirements to structure and behavior of domain objects. When we work with formal specifications, the main relation between specifications to provide semantic correspondence is inclusion, and there are different formalizations that implement this idea, from subtype relations, and Leonid Kalinichenko had focused on formal specifications calculus, based on abstract types. Then class inclusions inclusion can be used. Specification refinement mentioned in previous talk. And of course concept subsumption in description logic. When we work with abstract types, we can include consideration of structure of data, as well as correspondence of methods or services.
Nikolay, you have 5 minutes.
Oh, it's a bit. It's a kind of annotation approach that uses preferably relation of subconcept or subtype to make a make an annotation, and it is principle for work in simultaneously in several domains. When we talk about fair data, data notion may include different kinds of data, including methods as data. So in working in a domain, we should collect implemented methods that mapped to domain specifications, so we can search and have non-heterogeneous methods for already implemented for a problem solving. Also, we can support experiment approaches, because from formal specifications of domains we could we can select correlations, model them, and then use the same correlations to find specifications of observed data, and analyze difference of generated data and observed one. The role of research communities is principal for such approaches with formal specification. Specifications of domains, because development of formal specifications are expensive, so research communities themselves can develop them because they are interested in long-term using of specifications that solve their problems with heterogeneity, searching of implemented methods, searching of available data related to their research. And communities should collect implemented methods for reuse in other researches, and should represent their results in terms of domain specifications to make them interoperable. So the research life cycle becomes to be rotated around formal domain specifications, which solves many problems we mentioned in the beginning of my talk. Thank you.
Thank you, Nikolay. Are there any questions? Nikolay, I have one question or one comment.
I'll speak in the next section on Go Fair, and we've been doing some very practical kinds of implementations of Fair in different forms. And we've identified recently, I think, what we call the data stewardship planning tool as a kind of converger, because there are tools now available for designing your data stewardship plan that you can modify with domain-specific attributes. So you can create a data stewardship planning tool for a community like geophysics or for rare disease, and then projects thereafter that need to be planned and worked out and staged can have automatic access to the domain-specific specifications like this. So just that your diagram caught my interest because we see this as a very potentially important converger. Okay, if there's no further questions, then I guess we can break for lunch.
Yeah, sure.
And then we have instructions, I guess, for lunch.
Sure. I propose to have a 1 hour break for lunch. So we will start our next session today at 3 o'clock.